Sasrikal students, today we're going to start the chapter Gravitation in class 11th. So, before starting this chapter, you must understand the history behind the derivation of this formula, which you have learnt in 10th standard. F is equal to G m1 into m2 divided by r square. Well, we all know this is a formula proposed by Newton. Now, it's pertinent to know what happened before this, which led to Newton deriving this formula. Who else, whose all efforts were there behind deriving this great formula, which defines all the force of attraction between two particles in this universe and exactly measures the force in newtons between them perfectly. So there's a very big history, but then to summarize it, it starts from Polish Nicholas Copernicus. You must have heard about this name. Nicholas Copernicus. This guy has his contributions in science in different areas, Copernicus. Well, he suggested that planets move in circles, perfect circles. Planets move in circles around the sun. Now, when came the term around the sun, it was contrary to the popular Christian belief at that time. There was colonialisms, and a lot of countries were under the UK. So it was a common belief in political as well as scientific circles that the planets move around Earth as a center, which we have heard number of times has its roots in Bible. So as this was against the Bible, it was not really credited by the church. So then came Galileo. We all have heard about his love with the telescope and his fights with his wife because of his love with the telescope. Now this guy Galileo, there could be many who agreed with this Polish monk Nicholas Copernicus. But then Galileo was probably the one who came out openly supporting his belief that yes, it's true. Not just by intuition, but based upon his observations and possibly the first telescope made by him. So a lot of inputs this guy had in astronomy. So, but ultimately for Galileo also, ironically, it led to the prosecution from the state for the beliefs and the theories put forward by Galileo in support of Polish monk Nicholas Copernicus, that the planets and the earth move around sun, not the vice versa. Now, parallel to Galileo, there was another nobleman. His name was Tycho, worth mentioning, Brahe. There could be other scientists also, students, but then this name is very important, Tycho Brahe. This guy was this nobleman from Denmark, and he spent so many of his years recording observations of planets without state-of-the-art equipments we have nowadays. His data was analyzed very strangely by the one which we all familiar with the students as well as teaching community. Tycho's assistant name was Kepler, the complete Johannes Kepler, famous for Kepler laws, we all know. Tycho Brahe had a lot of observations, lot of data, and they were all obviously compiled by the person, thought upon by the person. But then at the same time, Johannes Kepler was his assistant, who was basically appointed to record the data, analyze the data also. And then guys, Kepler from 1571 to 1640. It was from this data student, by understanding the data and the patterns he observed in the data, he put forward those elegant laws which we are going to study, what are known as Kepler laws. Kepler laws of arbitrary motion, or whatever you say. And guys, now comes Newton and the gravitation law. Newton knew all these three laws very well. Means after studying from Kepler, after studying all the synthesis, all the analysis done by Johannes Kepler of the data of Tycho Brahe, Newton read it carefully, analyzed, comprehended, and you could say the nichode of this Kepler laws, the summary of this Kepler laws, or by this understanding of Kepler laws, Newton put forward his famous universal law of gravitation, which gives us the value of the force in newtons. The value of G determined experimentally separately by another scientist or physicist. I'm not remembering right now. Okay, this is the history of gravitation law. And in order to understand gravitation law and the beauty in it, that how it is derived, we need to understand Kepler laws. Obviously, in order to understand Kepler laws, you need to understand that data. But Tycho Brahe, you guys don't have so much time preparing for different competitive exams. So let's understand Kepler laws one by one. So guys, now we have three Kepler laws. Kepler laws. Now we have first Kepler law, which is known as laws of orbits. See guys, the person we started with, the Polish monk Copernicus, who was really criticized by the religious bodies at the time for blasphemy, for stating things against the doctrines of religion. Copernicus, great person, I would say. But then he stated, he postulated, but then he said that the orbits would be circle. But then research going on step by step, convergence, coming to more and more better results. Kepler did not agree with that. He stated that the orbits are not circles, but they are ellipses, elliptical orbits. And that really solved a lot of understanding in understanding the planetary motions. So what is Kepler laws, guys? It's known as laws of orbits. It says planets move in elliptical orbits. Move in elliptical orbits with Sun situated at one of its foci. So we have focus, singular, and foci. There are different pronunciations in different countries for this word. It doesn't really matter. But the meaning is same. But what's the meaning? Now this is basically a ellipse, students. This is basically an ellipse. Now, not able to draw perfectly. Now, guys, this ellipse is there, and this ellipse have two axes. We all know that, major axis and minor axis. Now, it has two focus. Now, where are the two focus? So one is here, and other is here. We name it F1, F2. So here the sun is there at one of the focus. Let's say sun is here, and now this is the circumference of the. This is the periphery of the orbit, elliptical orbit. This is your elliptical orbit. Now, you take any point T on this. You take any point T on this. How you draw the ellipse is also very interesting. See, guys, you take any point T on this orbit, you measure this distance, Tf1, and you measure this distance, Tf2. You have to draw a shape so that every point on that shape, in that closed curve, Tf1 plus Tf2 is a constant. If you draw like this with any center, F1 or F2, you will get a perfect ellipse. So in this ellipse, there will be any point, with this point also. So this distance and this distance will be constant. Talk about this point. Obviously, at this point, this distance plus this distance, is always same. But with this point, so this distance plus this distance is always same. So this is how the formation of ellipse is there, guys. Now, let's say this distance is 2b. We're going to use them in the numericals. All right, means I take this distance as b, so double of this is 2b, and this distance along the major axis is 2a. Obviously, this is a, right? And from the center of ellipse, and this point is a, double is 2a. So what I'm going to say is that, let's say this is BC, point B, point C, point P, point A. So PO, see that this distance is O. So guys, PO is equal to AO. Now, instead of giving focus on major axis, we give focus on semi-major axis. Why? Because this helps us in understanding third Kepler laws better. PO, this distance, is equal to AO, is basically your semi-major axis of ellipse. All right, guys. So now, special case. See, when F1 and F2 come closer, F1 and F2 come closer, and they merge with O, and then this ellipse converts into a circle. Why don't you guys draw an ellipse today in such a way that TF1 and TF2 is constant? You'll get a perfect ellipse. Okay. So this is your first law, that is laws of orbits. What is your second law of Kepler, students? Second law, Kepler's second law, or this is known as laws of area. Very simple. What is law of area? So guys, again we draw ellipse. Let's say this is the ellipse. Now let's say at one of the focus, this is sun. So let's see, this is a line joining what? It's line joining sun and a planet. So we have planet P, all right. And then we have Let's say in delta t time means small time, some measurable time, the planet from P moves to point P dash. Now, this is the line joining, SP is the line joining planet, any planet, okay? Not only Earth, any planet. This law applies to all the planets and the sun. The line joining planet P and sun, this line, it's changing its position. Let's say it's going in this direction. So it's sweeping the area. Now this is the area swept by the line SP when it moves in this direction anti-clockwise. So after time delta t, P comes at P dash, the planet. So the area swept by the planet, the line SP in time delta t is basically P dash. Now let's say at some other time the planet is here, and again in time delta t the planet come here. So same, this is again the area swept by the line joining planet in the elliptical orbit and sun. So this area is again P dash. I'm sorry, I've written this area as PAP. No, this is PSP dash. So I'm sorry. So this area, guys, delta A, in both the cases, is the area swept by the line joining planet and sun in time delta t. Second law says both these areas will be same. Both these areas are same. So how do I define second law? Well, it says line that joins what? Any planet to the sun and the sun sweeps equal areas in, can any student say equal? Can any student complete that? The line that joins any planet to the sun sweeps equal areas in equal what? Intervals of time. This is the observation, and this law comes from the observation, or you can say it's in line with the observation, students. The planets, when they are far away from the sun, let's say at point P, at this point they are near to the sun, the planets appear to, move slowly. They appear to move slowly as compared to when the planets are near the sun, making this area equal. So this is also a very, very important law. One thing I forgot to tell you, students, this, please come here. This point A, which is farthest from the sun, is known as aphelion. APEHEION. Aphelion. And the point, the location of the planet which is closest to the sun, so obviously it is this location on major axis, is known as perihelion. So this is like, you might have to listen to this video again, right? So these are the two laws of Kepler. And now we immediately go to the third law. The third law is law of periods. A lot of numericals based upon this law. So third law of Kepler is law of periods. Now to understand this, a simple prerequisite knowledge of what is time period is important. So I think students knows what is a time period. Time taken to complete one oscillation. or 1 revolution is time period, and 1 by time period is basically frequency. Take a unit of frequency, name after famous scientist Hertz, right? So this is in second time period. We know that. So what is law of periods? Periods means time period. So now guys, so it says the square of time period, the square of time period, the square of time period of revolution of a planet is directly proportional to what? The cube of semi major axis of the ellipse. Which ellipse? Not any ellipse. Ellipse which is traced out by the planet. So, Mr. Mitod Singh, can you repeat this law again? What is law of periods?
Both the square of the time period of revolution of a planet in this
Yes.
proportional cube
To the cube of
semi-major axis
axis
of the ellipse
traced out by the planet. So again, as I've already told you, these 3 laws came from all the data tabulated by the great scientist I've already mentioned to you. That was Tycho Brahe. So it was tabulated by his assistant Kepler. So tomorrow's video, we're going to really see how he got to this law. So in tomorrow's video, we're going to take that data, and we're going to see whether the square of time period, well, in the data, time period is given, and the semi-major axis is also given. So we'll take cube of semi-major axis, and we'll take square of time period, and we're going to see the square of time period divided by cube of semi-major axis. Let's say that is m. Cube of that would be a constant. How come? So it's like you say that you say that, let's say x is proportional to y. So if you want to get rid of this proportionality sign, you want to introduce equal to, you must introduce a constant k. Why you have to introduce a constant? Oh, this knowledge comes from mathematics. If this is a line, it's a straight line. Whenever we say x is proportional to y, means it is linear dependency. So, so on the graph, it would be a straight line. So here is y, here is x. So x is proportional to y. Where x is proportional, unless this line has a slope of 45 degree, the value for k will not be 1. The k will have some value. The constant will be there. What does that mean? X would be equal to something, maybe 1.5y, 3y. There is some constants. You have to introduce that constant. You don't really have to introduce a constant when your tan theta is 1. Here on this line, all the points will have same abscissa and ordinate. And hence I say, students, you understand maths well, you're going to be a good physicist. All right, guys, wait for tomorrow's lecture at 12 o'clock, and we discuss these Kepler laws in terms of mathematical calculations. Thank you very much.